Now that we have been introduced to the idea of the polyhedral model, we're going to try and develop a theory for affine transforms. And when we are going to talk about affine transforms, recall that in the polyhedral model, we are basically talking about affine loops, where the iteration space has some constraints, the accesses to memory through arrays have some constraints, and then also there is the angle of parallelism. And so to be able to capture this more formally, we're going to define three spaces. The first space here is the iteration space, and this basically represents the set of dynamic execution instances of a computation. So if I have a loop which says for I equals 0 to n something I plus plus and then something in the body, then there are n different dynamic instances, one for each possible value of I from 0 to n minus 1. And so these form the set of dynamic execution instances. If it's a depth 2 loop, it's a loop nest of depth 2, then maybe the first iterator variable is I going from 0 to n, and maybe the second iterator variable is j going from some other bounds, maybe 0 to m, in which case the number of dynamic execution instances are m into n, where I can range between 0 to m and j can range between 0 to n. And also, it's not necessary that this is a rectangular region. For example, I could say that for j equals I to m or something like that, and that would also be a reasonable affine space, iteration space that can be captured using the polyhedral model. In other words, this is the iteration space, which is the set of dynamic execution instances, is basically the set of combinations of values taken on by the loop indices. So if I have loop indices a, I and j, what are all the combinations of I and j that are possible in this loop nest? So in my example, it would be 0, 0, 0, 1, 0, 2 all the way till 0m, and now 1, 1, 1, 2, 1, 3 and so on. Okay, so that's the iteration space, and we discussed last time how the iteration space can be expressed as a convex polyhedron in a d-dimensional space for a d-depth loop nest. In other words, for d-iteration variables. We're going to see that in a little bit more detail today. Then there's a second space, which is the data space, and this is the set of array elements accessed. Recall that we are confining ourselves to loops where the memory regions that are accessed can be expressed as affine expressions of the loop iteration indices, surrounding loop iteration indices. And so, we can assume that these are arrays, because arrays also have a very regular memory layout. And so these are the set of array elements accessed, and that's the data space. And typically we would express the data space as a function, as an affine function of the iteration space, because that is our constraint for the polyhedral model, that the set of memory locations that are accessed can be expressed as affine expressions on the surrounding loop variables. In other words, the data space can be expressed as an affine expression over the iteration space. So if I just morph the iteration space using some affine matrix, I would get the data space. Once again, we're going to look at this in more detail in the coming modules. And finally, there is the processor space. And what do I mean by the processor space? So we are going to be interested, one of the things we're going to be interested in parallelization. We are going to want to map different points of the iteration space to different processors. For example, affine partitioning that we discussed in the last module. When we do that, we're going to create a map from points in the iteration space to points in the processor space. We're going to say that, okay, this particular iteration, let's say 0, 0 is going to execute on processor 2, and 0, 1 is going to execute on processor 1, and so on. And so we need some way of being able to represent the processor space. And so this is we're going to have a third space to be able to do this, and that's going to represent the set of processors in the system where each processor has been assigned a unique ID. Now, here's an interesting fact, that even the processor space we would be basically, in the polyhedral model, be representing as a affine expression or an affine function of the iteration space. So given an iteration space, we're going to have an affine function on the iteration space to identify what is the mapping. So the mapping from iteration space to the processor space is going to be an affine function. Recall, what is an affine function? Something that can be written as summation ci xi plus c0, where xi's in this case would be the loop iteration variables. Okay, once again we're going to see this in more detail in the coming modules. So for a d-depth loop nest, each iteration variable has a lower bound and an upper bound. This is a constraint that we're going to work with in the polyhedral model. But notice that these lower and upper bounds can potentially be a function of the iteration variables at lower depth. So for example, if I have a 2-nest loop depth, the first iteration variable is I for I equals 0 to n, and the second iteration variable is j, then I is the lower depth variable because it's at depth 0, and then j is the higher depth variable, it has depth 1. And so the bounds of j can be expressed as functions of iteration variables at lower depth. In other words, the upper bound and the lower bound for j can be functions of I in this particular example. And that's why these iteration space need not be perfect cuboids or rectangles or anything like that. They can be any potential convex polyhedron. And so this can be represented as a convex polyhedron, as we also saw in our last module. And recall, what is the definition of a convex polyhedron? If 2 points are in the polyhedron, that's this is the definition of convexity. If a polyhedron is convex, if and only if 2 points are in the polyhedron, then all points on the line connecting those 2 points are also in the polyhedron. And we saw an example last time. So let me take an example of a non-convex polyhedron to show the counter case. So here's an example. Let's say the first iteration, once again I'm going to use a 2D loop nest, and let's say the first iteration variable is x1, which goes from 1 to 6. Now this looks very convex, because if I take any point between x1 and between 1 and 6 and draw a line between them, it's also going to be between 1 and 6. But now x2 goes from minimum of 3, 5 minus x1, 1 to maximum of 10 minus 3x1 and x1 plus 6 by 2. Now this basically, I mean, I'm not going to show how how I'm going drawing this picture, but just take it from me that if I was to draw the iteration space for all possible values of x1 and x2, all possible integer values of x1 and x2 that satisfy these constraints, I'm going to get a figure something like this, right? So these different lines are basically representing all the linear combinations that I have. For example, x2 is greater than equal to 1. That's coming from the fact that the 1 present here, or x2 is less than equal to x plus 6 by 2. That's coming by x1 plus 6 by 2, and that's coming from this constraint here, and so on. But notice that this particular polyhedron that I get, or polygon that I get in a 2D space, is actually non-convex, because if I draw a line from, let's say, this point to this point, then there are some points in the middle that are not part of this polyhedron. So how did we end up with such a non-convex polyhedron? Well, notice that x2 goes from minimum of some values to maximum of some values. And so the constraints are no longer specifiable only as linear inequalities, because now I have to say that x2 is greater than equal to 3. Depending on what is minimum among these, x2 is greater than equal to the minimum of these things. And that's not specifiable as only a set of inequalities. On the other hand, if I was going from maximum of some things to minimum of some things, it would have still been possible to represent it as a convex polyhedron. In any case, here is an example of a convex polyhedron, and this is an example that we have seen before. For I equals 0 to 5, for j equals I to 7, some loop body, and this is the iteration space of this particular loop nest. I is going from 0 to 5, j is going from I to 7, and notice that this particular polygon is a convex polygon. Now, one quick check to figure out whether something is a convex polygon or not is that, can I write the polygon space that is covered by the iteration variables as a conjunction of inequations or inequalities? So in this case, I can indeed do this, because notice that I is greater than equal to 0 comes from the lower bound that I has a lower bound 0. So I is greater than equal to 0. I is less than equal to 5. So I has an upper bound of 5. J equals I. So J equals I to 7. So J's lower bound is I. And J's upper bound is 7. And so if I just use these inequalities and conjunct them, you take the logical AND of them, then what I will get is a convex polygon. So in fact, any conjunction of inequalities, affine inequalities, will always result in a convex polygon or convex polyhedron, even for a general d-depth loop nest. And one way to express these inequalities is to bring them in a kind of standard form, where we try to bring it into the form summation ci xi plus c0 is greater than equal to 0. And so in this case, this becomes I is greater than equal to 0. This becomes minus I plus 5 is greater than equal to 0. minus I plus j is greater than equal to 0 and minus j plus 7 is greater than equal to 0. Notice that I have, in my constraint, I'm mandating that it should be a greater than equal to inequality, and I can just rearrange my elements so that I always get a greater than equal to 0 on the right hand side. And I'm doing this so that I have an easier representation of these inequalities. And here is a matrix method of representing these inequalities. I just basically, this matrix basically forms a set of coefficient matrices, and these are the loop, this is the loop iteration space augmented with a 1 at the end. So I comma j represents the loop iteration space, and 1 is basically the constant element for which which captures the C0 part of our affine expression. And so if you read this becomes 1 into I plus 0 into j plus 0 into 1 is greater than equal to 0, and that's exactly our first inequation. And the second one is minus 1 into I plus 0 into j plus 5 into 1 is greater than equal to 0, and that's exactly our second inequation. And similarly, I have two more inequations corresponding to the two inequations that I have in the yellow color on the left. Now, this is a standard form of writing an affine space, a conjunction of inequalities, and such a representation also guarantees that what we get as a result is going to be a convex polyhedron. So all these things are interrelated, and this also makes the analysis of a program that behaves in this way easier and more higher level, and so we can do transformations related to locality and parallelism. So I'm going to use a standard notation to be able to represent such spaces, some such convex polyhedral spaces. And here is the notation. I say I with the underline, this represents the I vector, belongs to a d-dimensional integer space. So z here represents the set of integers to the power d. So I belongs to a d-dimensional integer space such that bi plus b, so b is a matrix which looks something like this. This is the coefficient matrix. Capital B is the coefficient matrix, and small b is the C0 part of my affine expression. So this column basically becomes small b, and this part here becomes capital B. All right, and so this is another way of writing the same thing, and basically say bi plus b greater than equal to 0. Capital B becomes the multiplier of the iteration space variables I, represented by the vector I vector, which in this example the vector I is ij. The coefficient matrix is, this first two columns, 1 0 minus 1 0 minus 1 1 and 0 minus 1, and small b is the third column, 0 5 0 7, which forms the multiplier for the unit elements 1, which basically represents the C0 of our affine expression. And so this representation here, I belonging to z to the power d, bi plus b greater than equal to 0, is guaranteed to represent a convex polyhedron, and you can represent any convex polyhedron using this representation, a d-depth convex polyhedron. And so we're going to use this notation for representing our iteration spaces. Okay, it is not enough, however, to just represent the set of iterations. We also need to encode their execution order. So it's not just enough to say that 0 0 is going to get executed and 1 1 is going to get executed, but we also want to know what is going to get executed first. So maybe 0 0 gets executed before 0 1, and 0 1 gets executed before 0 2, and so on, and we need to have some way of encoding that execution order. Now notice that there are multiple ways of arranging my I comma j. I could have, it's just a convex polyhedron. I could have switched I comma j to j comma I or something else, and still I would have been able to represent it using, just change my capital B and small b matrices appropriately to be able to represent the same convex polyhedron. But we just don't want any order. We want that particular order that is also going to reflect the execution order. And so we are going to encode an order in the I vector, I with the underline. And so this is going to be encoded in this way, and this is just a convention that we will follow, is that the execution order is the ascending lexicographic order on I. Okay, so for example, I could have said that so let's say 0 comma 0 is the first thing, and then 1 comma 0 is the second iteration, and then it is 0 comma 1, and then finally 1 comma 1. So let's say my iteration space is 0 0, and this is for, and let me just say that this is I comma j. I'm representing I comma j, and let's say this is my iteration space 0 0 1 0 0 1 1 1. Now it is not okay to basically use ij as the, is this the lexicographic order? So this is the execution order, by the way, right? So this is the execution order, and my question is this also the lexicographic order of I comma j? And the answer is no. The lexicographic order of I comma j is actually 0 0 0 1 1 0 1 1, because we first increment the second element, the least significant bit, before incrementing the more significant bit. And so I comma j is not encoding the execution order. In fact, I should probably make this j comma I, and then this would j comma I would encode this particular execution order, because now if I do j comma I, then I'm going to get 0 0 0 1 1 0 and 1 1, and this is going to be my ascending lexicographic order, and this is also the execution order that I desired. And so I'm going to use j comma I instead of I comma j in this particular example. In general, I'm going to encode the order by encoding the order of variables or choosing the variables appropriately, such that the order is encoded in the set of iteration space, and that would make my future analysis simpler. And because we also need this information of ordering, because if there are data dependencies, then we want to respect that particular order. So once again, we are going to encode the order in the vector of iteration variables I, such that the execution order is equal to the ascending lexicographic order of the iteration variables in I. Now, just for completeness sake, let me define what is an ascending lexicographic order. I think you should already know this. Let's say there are two vectors I and I prime. I is I1, I2, I3 dot dot In, and I prime is I1 prime, I2 prime dot 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 In prime prime. Okay, so notice first of all that n and n prime can be different. Okay, and this is also similar to our lexicographic order. In a dictionary, we can say that the word zebra is lexicographically comes later than the word, let's say, abracadabra, right? Even though abracadabra is a bigger word. So abracadabra, the n in the abracadabra is maybe 10 or something like that, the length of the string. Whereas zebra is, the n prime is 5, yet we can say that abracadabra is lexicographically less than zebra, right? And so the definition of lexicographically ascending is identical. I is lexicographically less than I prime if and only if there exists some index m, so some index m here, let's say m, such that m is less than n and m is less than n prime, such that all the elements till m are equal, so these are all equal, and the m plus 1th element is less. Okay, and this is exactly what the dictionary order says, right? So if I have to compare, let's say, abracadabra with ABBA, then I say A, it's equal, then I look at B, it's equal, and then I look at the third character or the third variable, and that is B in one case and R in the other case, and so we say ABBA is less than equal to, is lexicographically less than abracadabra. And so that's exactly what's going on here. We basically look for the first different element, and then we check which one is less among them, and that particular string is going to be less than the other one. And that's exactly the ascending lexicographic order in the iteration space as well. Now, one last thing. How about loop invariant variables? So far my capital B and small b, I have said that they need to be constants. But what about I equals 0, I is less than n, I plus plus? Here n is neither a loop iteration index variable, nor is it a constant. How do I capture that? Does it fit in our framework or our representation of I belonging to z to the power d? Here d is just 1, so I belonging to the set of integers, such that bi plus b is greater than or equal to 0. Well, it does. We're just going to extend our small b such that it can also have loop invariant variables in it. So for example, this would be in the value, in this representation, these would be the matrices b, capital B and small b, and this would, and I would be just a single dimensional vector. capital B would be 1 and minus 1. So this basically, and small b would be 0 and n minus 1. So this would basically say, so the first row is going to say I is greater than equal to 0, and the second row is going to say minus I is greater than equal to n minus 1, which basically translates to I is less than equal to n minus 1. Probably I should have said minus of n plus 1, and that would basically translate to I is less than equal to n minus 1. So even for loop invariant variables also, this representation would work. We just need to basically allow the addition of loop invariant variables, find some expression on loop invariant variables in the vector B.